In this video I'm going to show how to compute the moments of a Lognormal distribution. To do this I will recall the concept of moment generating function of a normal distribution and show the link with a lognormal distribution. Finally, there will be space to understand how a change in the parameters of a lognormal distribution will affect its shape. So we start by defining a random variable x tilde, which is normally distributed with mean mu and sigma square. Then the definition of a log normal distribution, it is that it is the exponential of a normal distribution. The exponential of a random variable should remind us the concept of moment generating function. In fact, the moment generating function is the expected value of the exponential of j x, which is the jth moment of the log normal distribution. And then with this relationship we can compute simply the moments of the log normal distribution. We recall the moment generating function of a normal distribution, which is the exponential of j multiplied by mu plus j squared sigma squared over 2. Therefore, the first moment, we take it here so that you don't have to go back to the previous recording. Therefore, the mean, it is the moment generating function computed with j equal to 1. Then the variance, it is computed by using the shortcut formula, which is the second central moment, the difference between the second central moments and the first moment power 2. By simple algebra we can arrive at the final result. Then the standard deviation is simply the square root of the variance, and with this setting we can see that the first bit is equal to the mean of log normal distribution, and then finally we have the coefficient of variation, which by definition is the standard deviation divided by the expected value, and therefore it is simply the square root of the exponential sigma square minus 1. The coefficient of volatility, as we will see in the next slide, is crucial because it is present also in the formula of the skewness, which in this video, for reason of complexity, I do not show here. Therefore, it is this formula, and the second bit it is the coefficient of variation, volatility, and then also in the first member we can see by taking a careful look that if we add the subtract a 1, we are able to obtain the coefficient of volatility power 2, and then we have a 3, and therefore with this result we are able to understand that a higher coefficient of volatility, which is given by a higher standard deviation or a lower mean, will impact the skewness of the distribution. Therefore it will have a heavier tail on the right hand side of the random variable. Then here we show that how a change in the parameter, for example sigma, have an impact on the shape of this distribution. Therefore, if we increase sigma simply by reasoning, we can see that the coefficient of volatility increases, and therefore by increasing the coefficient of volatility, it means that we have an higher standard deviation with respect to the mean, and therefore, and finally, we will have an higher skewness. In fact, this is the result that the distribution is less taller respect to the first one, and there's a bigger tail on the right hand side. Thank you for your attention.